Hello, everybody. Welcome back. Good morning, and hope you're all doing really well, staying safe and healthy and everything from these fires. I don't know. Hopefully, none of you guys are affected, but if you are, just hang in there, and I'm sure it'll be okay. But sorry for that. At any rate, we got about a minute, and then we will start off our meeting today. Hey, Jamie. Everybody else, feels good to see you guys. Let me know if you're here. Hey, Ruby. Hi. Hey there, Arlene. Cool. Good morning. Hey. Okay, just a moment. Hey guys, Isaiah, Leo, Marissa. Good to see all you guys here. Cool. All right. Well, welcome back. It's now 11:30. Thanks again for being here. And today we're going to just continue working through more of these practice problems. I have also some new derivation rules that I'm going to try and teach you guys about today. Notice that I sent an announcement last night to the class, just informing you guys that the exams have been all graded, and you can ask for your grade for that or for anything else whenever you want. Just have to send me an email, and I give individual response to any email I get. Sometimes it takes me a day or at most 2 days to respond, just because I have a lot of classes and a lot of emails coming in, but I definitely will reply to any question about any grade. So as far as the class is now, we're halfway through it. You're working on your third homework. It's due in a week from today. And then after that, there's just one more homework and the final exam. So yeah, and make sure to continue attending the meetings. You know, attendance is kind of sometimes more, sometimes less, but this is the most critical part of the semester for you to focus hard, because the information kind of just piles up, and it's like, I don't know if you guys have ever had that experience in a math class where you just kind of like lose your focus for a week or something, and then you come back to it and you're like, whoa, the class has moved on so fast, and now I'm kind of not up to speed anymore. You don't want that to happen to you, so stay on top of it and make sure to keep coming to the meetings. You know, I mean, that's on you, but you know, I can't make you do anything you don't want to do, but I hope you just want to come to these meetings and do your best. Okay, well, thanks again. So, like I said, those that are interested in any of their grades, just check with me, and I've got them ready for you at any time. But we move on now to some more information. Let me go ahead and, I'll just start today's meeting without using the Zoom for a minute, and then when I'm ready to do some practice problems with you guys, we'll go back and I'll give you the Zoom link so that we can do our dual platform thing. Okay. Just plug this in here. Charging cable. Okay. So we've learned a certain number of derivation rules so far. We've learned conjunction introduction, conjunction elimination. We've learned reiteration rule. We've learned conditional elimination, biconditional elimination. And we've also learned disjunction introduction. But we've still got to learn a couple of these rules that are involving what are called subderivations. So today I'm going to try and teach you two more of the inference rules, conditional introduction and biconditional introduction. Okay, now let's start with the conditional introduction rule. And here's how it looks. Okay, the conditional introduction symbol is either horseshoe letter I for conditional symbol introduction, or because we use the arrow also, this is another way to write it. Arrow, single arrow I. Okay, so that's like what gets written in the justification column within parentheses. And here's how the rule basically looks. So suppose that in a proof, you want to not eliminate a conditional, but create one. Suppose you want to establish some if-then statement. Like you want to create, or as it is, introduce a conditional to the proof. Here's how you do that. Okay, so you have to create a separate ledger line from the primary assumption line of the proof. That means that you just indent over slightly and you create a second vertical line. You write the letter that you would like the conditional to start with. So just schematically, suppose that you have assumed P. Now, if you continue this, what is called subderivation structure, and you make inferences and you keep adding inferences, if you eventually get to, let's say, the letter Q within this subderivation, then you can close the subderivation. And outside the scope of this scope line, you would write P horseshoe Q, or as we have kind of become accustomed to, P arrow Q. I'm just erasing and putting the alternative symbol because this is kind of our more common symbol in this class. So if you've got the assumption of P, and then you are somehow able to establish within the scope of that assumption the statement Q, when you've arrived at that desired consequent, you close the subderivation and you write the conditional which starts with this as its antecedent and which finishes with this as its consequent. In other words, P then Q. Let me kind of explain how this could work with the concrete example. So I'm going to write out an argument here in English, and then we're going to try to translate that argument and do just a very elementary proof involving this new rule. Okay, so suppose we've got this argument here. If Wendy is on the Eiffel Tower, then she's in France, or sorry, then she's in Paris. Okay, and suppose we also say that if Wendy is in Paris, then in that case she's in France. And suppose we want to prove from these two statements that therefore, conclusion, if Wendy is on the Eiffel Tower, then in that case, she is in France. Okay, so first thing we're going to do, we're taking this slow, we're going to try and translate these statements, okay, and use logical symbolism to do that. What's up, Arturo? Question from you? You say you have a question? Let me know. If you do have one. You say you have a question. Well, maybe you'll get to it, and whenever you do, I'll take it when I see it there in the chat. But do let me know. Anyways, though, we need to translate these sentences here into our logical symbolism. So let's try and do that. Tell me what sentence letters I can designate to stand for parts of the sentence here in letter 1, or in question 1. Premise 1, thank you, sorry. In premise 1, I just need a couple of sentence letters so that I can translate that. So just hit me with a sentence letter and the information that it stands for. Go ahead. It says if Wendy's on the Eiffel Tower, then she's in Paris. So we need to designate sentence letters and connectives to translate this into our logical terminology. So let me know what's one sentence letter that I can use to start to convert this into the symbols and sentence letters we have. Okay, W, Marissa. W stands for what? Tell me just what statement W stands for. I think I know, but there's many things in this that involve the term Wendy, so I need to know which one you're thinking of. Whenever you designate a letter, you have to tell me the sentence it stands for. Okay, Wendy is on the Eiffel Tower. Okay, good. Not the word if, though, Kilaya. The word if is not to be stated in the symbolization key, because if and then are dealt with by means of the arrow symbol. So you don't say if, you just say Wendy is on the Eiffel Tower. Okay, but that's not the only sentence letter that's needed. So there's more. W's a fine start, but we need that if W, then she's in Paris. So more sentence letters. P, Wendy is in Paris, okay? Okay, and there's still one more. F, Wendy is in France. Okay, good. Okay, WPF. Now, let us then erase the English written version of this and just describe it in logical symbolism so that we can talk about it in a logical way. So what it did say is that, first of all, if Wendy's on the Eiffel Tower, then she's in Paris. So that is if you said W for Wendy's in the Eiffel Tower. If W, then what? What's the first sentence? Which said if Wendy's on the Eiffel Tower, then she is in Paris. What should that look like logically? Our first premise here. I started off telling you that W is the first thing, but what should it say overall? That first premise. W arrow P. Good. This says that if Wendy's on the Eiffel Tower, then in that case she's in Paris. That's the first assumption, the first premise. The second premise was what? That if she is in the Paris, then she's in France. Now how does that look logically? P arrow F. Okay, good. And now assume that you're told to derive the conclusion that was stated before. So what would be the conclusion that it said falls below? And that's what we need to derive by means of inferences. But what did it say? It said that if W, then F. Okay, good. So this is our goal right here, W arrow F. We have to somehow get to that result from these two initial premises assumptions. Okay? Now this little horizontal line is just the breaker that divides whatever the assumptions are from the inferences that follow. And ultimately what we want to do is do inferences by means of these rules until we arrive at that result there. Okay, so now I'm going to tell you guys how does this conditional introduction rule work. So here's our goal, W arrow F. When you have a conditional that you want to prove and you want to get to the result of a conditional sentence where the main connective is the horseshoe or the slash, the arrow, then you have to do conditional introduction. So how it works is you start by assuming just the antecedent of the conditional that you want. And when you do that, you create this what's called subderivation. Notice that I've moved over from the leftmost vertical line and I've created a secondary vertical line that begins here. And I've also established like this horizontal breaker in between the assumption and the remaining steps in the subderivation. So what we write is W here, and this is assumed for conditional introduction. Okay? Now this W is not derived from any of the previous numbers, so you don't cite a number when you're doing conditional introduction. You just write the letter A, which is short for assume. We assume W for the sake of conditional introduction. Now, the next step continues in the subderivation. And the subderivation continues until we eventually get F. So now we have this new goal. Internal to the subderivation, we are trying to find a way to reach the consequent that we have to have in the overall conditional statement that we're trying to build. So it's like start with W, and if your goal is W then F, you have to continue through this until you get to F. So then, what could be an inference, anybody, that will add another step to the proof on line 4? Now we have 3 things to work with. We have the first 2 assumptions, but we also now have the letter W, which we have assumed. So what follows next? Since we have this new thing W, that gives us more options in terms of what to infer next. So tell me what you think could be the next step of the proof. The fifth step, or sorry, I mean to say the fourth, step 4. What is my new inference on line 4? There's really only one thing pretty much that you're able to do at this point in the proof. So think back to our earlier inference rules and make a quick statement to me about what's the next inference. Where do we go from here? Our goal is to get to F. But Frida, you say, wait, can you explain the citation for the third line? Yes, the third line is making an assumption for conditional introduction. We are learning this new rule, conditional introduction. How it works is that you assume the antecedent of a desired conditional. After that, if you are able to establish the consequent of the desired conditional, then you stop the subderivation and you write P arrow Q. P is the thing that was assumed as the antecedent. Q, in this case, is the consequent that falls within the scope of the subderivation. Here we've done something exactly parallel. We are assuming W because we want to get W arrow F. So we continue through this subderivation until we reach F. That's what we have done. Line 3 is an assumption of W. We're assuming W because it's the thing on the left of the result that we are told to derive. So in case you have to derive any conditional, if you are ever told derive A arrow B, if you are told derive A and B arrow X, or any arrow statement, any conditional statement, you always have to start by assuming in the proof the antecedent of the needed conditional. So since this is what is needed in the end, we have to begin by assuming the antecedent of it. But this is new information, so it's going to come out more clearly by means of going through the proof and just flying blind for a minute and just making inferences. Once we get to the solution, we will see how it works by looking back. Tanya, would P be the consequence? Yes, but tell me the rule that lets us have P. Well, it's the inference. The next inference gets us to P. Okay, good, Arlene. P comes from conditional elimination 1 and 3. Are we all clear about step 4? Step 4 was obtained just by using this to eliminate the conditional on line 1. Conditional elimination, if you remember, is where you have a conditional, and on a subsequent or other line, you have just the antecedent of it. When we added W to the proof, that allowed us to eliminate this and get P. And now another move is available as we continue, because continue until we get to F. And we're almost there. So what can be the fifth step of the proof? The fifth step of this proof. You know, now that you have P available. Oh, Arlene, you see it clearly that it's F. F comes from conditional elimination of 2 and 4. Step 5, any questions about step 5? Step 5 is just another use of the conditional elimination rule. And again, you shouldn't be too confused. When you have a new thing that's added to the proof, after P was established, then you have to go back and look at all the other earlier lines and see, is there anything that I can do with this new line of the proof? Since you now have P, you have to scan line 1, 2, and 3. And you'll see then that on line 2, the letter P also occurs. That's where you would notice that you eliminate that in order to get F. So the goal of the subderivation here was to assume W and eventually arrive at F. And we did it. We assumed W, and in 2 more steps, F is within the scope of the subderivation. So that means we close the subderivation, and we write the full conditional now outside the scope of this broken vertical line. And what it says is W arrow F. That's the end, and here's how we cite the justification. We say this is based on conditional introduction, and then we cite the series of lines that all fall within the scope of the subderivation. So that's 3 through 5. You see 3, 4, and 5 are all part of this little structure called a subderivation. So conditional introduction lines 3 through 5. I'm sure that's easy to read, sorry. Conditional introduction lines 3 through 5. And that's the proof of this one. So kind of reasoning in English, as we've translated it, let's go back and talk about it in English. So if Wendy is in Paris, sorry, if Wendy's on the Eiffel Tower, then she's in Paris. If Wendy is in Paris, then Wendy is in France. Prove that if Wendy is in the Eiffel Tower, then she's in France. Okay, well, on line 3, we say assume that Wendy is on the Eiffel Tower. Assume W, which is what that stands for. If we assume that she's on the Eiffel Tower, then since if she's on the Eiffel Tower, she's in Paris, we can conclude that she's in Paris. Now, on the basis of the assumption that she's in the Eiffel Tower, it follows that she's in Paris, and from that in line 2, it follows that she's in France. So when we assume that she's on the Eiffel Tower, it only takes a couple of inferences to show that she would then also be in France. That allows us to close the subderivation, and this is the result of that, that if she is in the Eiffel Tower, then she's in France. To me, the letter W is not the best choice, to be honest, because every time I see it, I keep thinking just Wendy. But Eiffel Tower is E, and I would have chosen E. But anyway, with the lettering that we have, this is the correct answer. Karina, so that's line 3 through 5, yes. The subderivation is lines 3 through 5. So you write a dash instead of a comma. And the dash stands for 3 and all the lines in between 3 and the final number 5. Sometimes the subderivation has more lines than just these. And in that case, the citation would be different. It would just be the number of lines involved in the particular subderivation of the proof. Okay, in this case, it's 3 through 5, but it can be something different in another case. Okay, so that's like just one example of conditional introduction. Let's see. I want to also give you the knowledge about what biconditional introduction is. So let's talk about biconditional introduction too. Okay. So one more little inference rule for today's lesson is biconditional introduction. And the symbol for that is two options. It's either triple bar I or double arrow I. I'll probably use the double arrow most often. Okay. Wait, sorry, Andre. You say, I think you forgot E in the citation for line 5. So what's the question? Sorry, you say that E was not cited in the citation for line 5, but there's no letter E. Let's go back to that proof again. So what we have here are these two things. For the moment, just hold that to the side. You had that if W, then Paris, if Paris, then France, and you're told derive that if W, then F. Okay, you have these two assumptions. And that's the result that you need to get to. So we start by assuming W. W, assume for conditional introduction. On line 4, now that W is in the proof, we can eliminate this conditional on line 1, resulting in P. So that's conditional elimination, lines 1 and 3. On line 5, this is perhaps where you say I was missing letter E for elimination. Okay, good. P eliminates line 2 and gives us F. So that's conditional elimination, thank you, of lines 2 and 4. Now that W has led to F, on the 6th and final step, it's W arrow F. And that is conditional introduction, lines 3 through 5. Okay, thank you. Now, Arlene, on line 3, what is your question? On line 3, does that say A arrow I? A arrow I. Assumption for conditional introduction. A means assume. E means eliminate. When it's in the justification column, yes. In the justification column, the letter E always stands for the full word eliminate. And A stands for assumption. That is correct. Okay? Arlene, on line 3, does that say A arrow I? Yes, it does. Okay, good. John Strong is another person that's, I don't even think in the class. Okay, so I was now going to show you biconditional introduction. Thank you for that. Okay, so biconditional introduction, another inference rule, goes as follows. So suppose that, go back a bit here in my notes. So we've got here a biconditional that we want to build. Biconditional introduction is just kind of like two applications of conditional introduction. So suppose that we have some sentence P, and then we get to the letter Q within the scope of the subderivation. No problem, Karina. And then suppose that after this, we start a subsequent subderivation. So there's a broken space in between these two vertical lines. But then we assume Q, and we infer R within the scope of that subderivation. If we've done this in these two subsequent steps, that allows us to say that P triple bar Q. Sorry, I meant to write the letter P here. P triple bar Q. So if P leads us to Q, and then in another assumption, Q can lead us back to P, from the conjunction of these two subderivations, we've now proven that P if and only if Q. So you have to do two subderivations for biconditional introduction. Now let me show you how that could work in an exact case. So suppose that all you have here is this assumption. And what it says is A and B. Okay, and now I'm telling you derive A double arrow B. A if and only if B. Okay? So what you have to do now is build a biconditional. You have to introduce a biconditional. And you have to do it according to this rule. So just so you understand, you have to assume the left side of the biconditional, then prove the right, and then assume the right side of the biconditional, and then prove the left. So it's also fine for you to do it in the other order, like assume the right and prove the left, but either way you go, you have to do those two things. So tell me what I shall assume now on line 2. I have to make an assumption of one of the two sides of this biconditional. So which shall I assume? Tell me then what I shall do on line 2 to start the biconditional introduction rule. Let's see. Just follow the form that you see here. If I want a biconditional with the two letters A and B on the left and right, then I have to assume one of those letters, and then from there make progress towards the other one. So what can I assume then on line 2? Just tell me. Okay, assume A. Very good, Jamie. We assume A, and over here the justification for that is assume for biconditional introduction. So this is a double arrow letter I. Assume for biconditional introduction. Okay. So what's the goal now? Since we have assumed A, what is the goal within the scope of this A assumption to obtain what other result? From A, we're trying to get to where? Tell me that. B, correct. Exactly, Karina, Amaya, Jamie, and the others. Yeah, we now need to get to B, and we can. But there has to be an inference that puts B in the scope of the subderivation. So tell me then, what shall I do? How do I get B? No, you don't assume B. No, but there's a way to get it. No assumption. We'll assume B later. But for the moment, we just need to get it within the scope of the subderivation. Okay, good, Leo. B is the result of taking that from this conjunction. B, conjunction elimination of line 1. Okay? Can we all see how B is something that was just stripped off of line 1? Because line 1 is a conjunction. Whenever you have a conjunction, conjunction elimination allows you to take something away from it. So we are able to take B off of that conjunction, and that's that. So the first half of our little journey towards A double arrow B is done. But we have a second part. Part 2 is that we now have to assume what other thing. Now, Karina, maybe your comment will come into play, but let's just get it out there in the chat. A second assumption now has to be made, and that's right, Amaya, it's the assumption of B. So we have to go back the other direction now. Assume that for biconditional introduction. Okay? So now what's the goal within the scope of this B assumption? What's the goal internal to this B subderivation? There's a big derivation, and then these are called like little subderivations. So within the scope of this little subderivation, what is our ultimate objective? We are trying to reach what result internal to the second subderivation. Like you can see in the first one, we had A and we wanted to get to B, which we did. Now we're trying to get back to A, correct, Arlene? And you say that it comes from conditional elimination on line 1, which is true. Okay, so now look. A led us to B. B, a second subderivation, led us to A. When you've done those two things, now you are done with biconditional introduction. You show at the end of that, outside the scope of these two subderivations, the expression that you were trying to build. And what is that? Well, it is A, double arrow, or triple bar, B. And here's the citation that you have to give. You say biconditional introduction. Sorry, I gotta get the symbol right. Biconditional introduction, and then what you do is you have to state the two series of lines where the two subderivations are. So that's 2 through 3, comma, 4 through 5. And that would be our total proof of this biconditional statement, just using those two things in the beginning. Okay? So are there any questions about any individual step of this proof? If so, do not worry, just feel free to ask. And if you have that question, I'd like to answer it, but I'm just trying to explain to you how the rule of biconditional introduction works. So today, 2 through 5, Jamie, no problem. So we've got a goal that we are told to find, which is a biconditional, A, double arrow, B. Whenever that is the goal, often you will have to use biconditional introduction. And the way the rule works is you look at this statement that you're trying to build, and you start by assuming just the letter on the left. That's why we did this on line 2, okay? Because we know this is what we want, so we always then have to just start by assuming the left term. Now, we start what's called subderivation after that, and within it, our goal is to reach the other side on the right, okay? So the other side on the right is the letter B. And B can be derived from taking it off of line 1 using conjunction elimination, because this is a conjunction. B is on the right part of the conjunction. So conjunction elimination on line 1 gives us B. A, therefore, has led us to B. The second part, part 2 of biconditional introduction, is to assume the other side then, in this case B, and then in parallel fashion, make inferences until we reach the other left side. And so we did that again, assume B, disconnect A from line 1, and now we have A within the scope of the B subderivation. A leads to B leads back to A. So since those two things have been completed, we then are able to close the subderivation and write the biconditional statement. Here, let me see. Evelyn, how come you didn't put an A before the double arrow in line 6? No, because this is no longer an assumption. This is the output of doing the assumption. So on the basis of these two assumptions, this has been proven. When you close the subderivations in biconditional introduction and in conditional introduction, you don't write the letter A over here in the justification column. You only write the letter A on the initial assumption that starts the subderivation. Okay, Evelyn, so that's that answer. Yes, and Tanya, you've said the same. Exactly. On line 6, it is not an assumption. It is something deduced from earlier lines that have already been made assumptions. Jamie, I mean for the citation, instead of 2, 3, 4, 5, can't you say 2 through 5? Oh, I understand. But that, okay, I see your question now. I was not looking at that. But, okay. Can you say 2 through 5? I thought you meant, can you explain the steps involved? And you're asking me why there have to be a comma between the two series. Because this indicates where one of the subderivations terminated and where the other one did begin. That's just part of the citation justification rule. I guess it's possible in a certain case for them not to run continuously. Like you could have had one subderivation and then done some random inferences before starting the second one. In that case, there would be a break in the two series of numbers, and then that would demonstrate the necessity of having the comma in between the two dashed series. Okay, so just understand that it's not a big deal, but yeah, you will have to put a comma in between the two dashed series. That's right, Jamie. Okay, let me try another one here with you while we're on the topic of this type of proof. I'll use the other symbolism just to kind of make that familiar to you as well. Okay, so, and then yeah, thanks, Jamie. So suppose again that your goal is derive a, let's say, triple bar B, same thing as double arrow. And now here are the two assumptions. A on line 1, B on line 2. Finally, now you're going to learn how to use the reiteration rule. Just spoiler alert, but anyways. So once again, the first step of this now is to do what? Assume blank. What's the first assumption now to make on line 3? Tell me, what do you think? First assumption to make on line 3. It's the same format as before. So the steps used in the previous examples follow again. Okay, good, Jamie. Assume A. Now, what's the justification? Tell me. Assume A, yes, good, Samir. But in order to, what's the justification for that? You will write blank, blank in that right-hand blank space here. What's the justification for giving A? No, not repetition, not yet, Evelyn. Hold on for that. Because it's an assumption. This is a subderivation, so it's not just something that's repeated yet. Assumption biconditional introduction, correct. A for triple bar introduction, since I'm using triple bar this time. Okay? What's the goal now? It's to get to B. Well, how can we do that? Sorry, Leo, I'm just saying never mind, but there's a fact about the letter R that is going to come into play here, but let's just get everyone on the same page. How do I get B here into line 4? Because again, with biconditional introduction, you have to do that pattern. You assume the left side, try to find the right side through steps. Okay, so yeah, you say B, reiteration of 2, correct. We have not used the reiteration rule before, so this is new for us. Reiteration, you guys remember what? It's just you're able to repeat on a new line anything that's available in previous lines. And since B is available on line 2, we can reiterate it into the scope of that subderivation, and that's good. So we've done half of the mission. A to B, no problem. But we're not done until we do the other side, part 2. So then tell me then, Frida, you're saying assume for biconditional introduction, but assume what? What is line 5 precisely? The thing to write on line 5. The sentence to write, and then the justification. Assume B. Okay, good. Assume for biconditional introduction. Okay. So what is on line 6 then? You tell me what is to be written. Evelyn, you say, I don't understand how for line 1 it's biconditional introduction. What line? You're saying line 1? Line 1 just says A. Or do you mean line 3? Well, you'll follow up with your follow-up there, but to the others. Oh, 3, Evelyn? Well, because that's just an assumption. We assume A for the sake of creating that biconditional. When you want to create a biconditional, you just assume out of nowhere the left side of it. The left side of it says A. So yeah, you assume that to start off, and you write assume for biconditional introduction. Okay, so line 6 to the others. Line 6 is A, reiteration of 1. Yes. Because the process of biconditional introduction requires you to go through specific steps. You have to start by assuming the left side of a needed biconditional, and then within the scope of that subderivation, get to the right-hand side. Afterward, you make a secondary assumption of the right side and show that that can trace logical implication to the left side, namely P. P goes to Q, Q goes back to P, then we close the two subderivations and we write the full biconditional at the end. In this case, the goal is A triple bar B. Two premises are given as just freebie assumptions. And now you start and you assume A with the goal of getting to B. But B is easy because it's already on line 2 and it simply gets reiterated. Same on line 1, we have the other thing, A. So when the second assumption of B is made, we can reiterate it. Therefore, what's the result on line 7? Line 7, we can now sort of finish it up. What is line 7 going to say? It will say A, you're saying double arrow, yes. And I'll just, because I'm doing it this way on this proof, A triple bar B. And that is on the result or basis of biconditional introduction, 3 through 4, 5 through 6. Good. Sorry, 3 dash 4, 5 dash 6. Okay. So I'm just doing another example of biconditional introduction, which in this case shows you how reiteration finally gets used. I'm sure you were thinking, well, why do we learn reiteration when no one's using it? Now it's definitely used heavily, and it's used in any case where you have to place in the scope of a subderivation some information that's available above in the proof. Okay, so we got some practice problems then that I just kind of want to go through with you guys so that we can continue to build up familiarity and skill with these subderivations and with these new rules. Lily, do we always have to start with the left side? No, not strictly. No, it's possible to go right to left and then left to right. Although I think that for most people, just reading left to right and so on, that just sort of makes more common sense. But yeah, it's okay to do it the other way. Okay. So now that we've done just some learning of these different derivation rules, I will, I think, put up the Zoom, and then that way I can call your attention to certain problems in the book that we can see on the screen all displayed at once. So here is the link. Go ahead and click that one, and I'll be right there with you guys. Okay, anybody with mics on, maybe mute for just a moment. And if you have another window open with me talking, you can mute the other window just to avoid any kind of noise interference. Okay, so I'm going to share the screen here. Yes. Sorry, I have to end the meeting for a second and start it again because I just updated my MacBook to OS Catalina, and therefore it requires me to close the app while it gains permission to access my microphone and camera. Oops. So 1 second, guys. Hold on. Okay. Is this working? Can you hear me? Let me, sorry, put on the chat here. Oops. Okay, great. Thanks, guys. Sorry for the slight delay and interruption. Come on back, everyone, if you're not here. Thanks. I just had to briefly close and reopen the application. Okay, sorry. So now we will share the screen. Okay, we're screen sharing. Thanks. And Logic book. Okay, and so you'll just see here within the text the rule of conditional introduction and a quick explanation and sample of how to do it. In this case, they gave you A, then H. That's the goal. And if you have these two assumptions that you're working with, you begin your first inference by just assuming the antecedent. That's how conditional introduction works. You want a conditional, you have to assume just the left part antecedent, and then eventually obtain to the right part. In this case, just like with if she's in the Eiffel Tower, then she's in Paris, then she's in France, assuming A, we're able to then eliminate the conditional here, which gives G. And then now that we have G, which was the consequent on this side, we can use that to eliminate the second conditional, get H. And then we close the subderivation, and you see the citation over here. Okay. Now, biconditional introduction is demonstrated and shown right here. If P is assumed and then Q is obtained, then that's half. The second assumption is Q, which leads to P, and if we do both steps, then we can obtain P double arrow or triple bar Q there at the bottom. Now, I have some problems to try, and it's on 5.1.2. So I just got to scroll down to this. Okay. Let's then try to get these results here. Okay. 5.1.2. Okay, good. So here's our problem. It's this one that you see on the bottom. I'm trying not to showcase the whole proof because I don't want you to know the answer just yet. Here we have to derive this conjunction. The conjunction says both A then B, both if A then B, and also if A then not D. That's the goal. That's the goal sentence. And you've got this one assumption that you have to work with, which is if A, then both B and D. B and, sorry, not D. So that is our assumption. Okay, so look, we got to prove this. What is this statement? What's the main connective of this statement? It is conjunction symbol. But it's a conjunction of two conditionals. So, you know, if we can build these two conditionals, then we can conjoin them using conjunction introduction. So, oh, sorry, let me pull up the chat again. Make sure that's clear to see. Okay, here we go. So just let me know, anybody, what do you think shall I do on line 2 to get this proof started? I have to make progress towards this big conjunction. And like an intermediate sub-goal on the way to this final result is just this and just this. So I have like kind of two sub-goals on the way to the big goal. I got to get this, and I got to get that. So let's try. What do you think I can do on line 2 to begin this proof? And, you know, obviously it's going to have to do with our new rules that we're learning, because that's what I'm trying to drill today. Okay, so Lily, you say write down A and assume this for the sake of conditional introduction. Good. So when you make the assumption, you have to indent over, and you write the antecedent of the statement you're assuming. So that's assumed for, wait, yeah. Did I get that wrong? Thanks. Yeah, there's a right-hand parentheses there. Thank you. Assumed for conditional introduction. Make sure that that's clearly shown. Okay, so we've assumed A for conditional introduction, which now, hopefully you see, enables further inferences. On line 3, in particular, what do you think can be the next inference? There's really only one option. Who could tell me what to infer on this third line? Now that A is present from the assumption we made, if you look back at line 1, there should be a move. There should be an inference that strikes you. So please tell me what it is. No, it's not B. Because think about it, B is not the whole, B is just one part of this consequent. The consequent is the whole conjunction here, B and not D. So B does not result. Go ahead, just let me know what inference to make to take that step on line 3. Okay, Nathaniel, very good. B and not D. B and not D from conditional elimination 1 and 2. Is anybody confused about where this came from? This third step. Well, all we did was, having already assumed the antecedent of this conditional, which is A, we then noticed that it matches the antecedent of this conditional on line 1. And that allows us to eliminate it and get to the right side, which is that full conjunction. Okay, who can tell me what is the goal within the scope of this subderivation? We opened it with A, but where are we trying to steer it towards? This subderivation for conditional introduction. What ultimately are we trying to get to? Why would it be conditional elimination, Jamie? This sentence here? Because line 1 is a conditional. Okay, Jamie, what kind of sentence is line 1? Can we see it? Can you see that it's a conditional? Because this arrow is the main connective, all right? How does conditional elimination work? Conditional elimination works where you have the whole conditional, and then on another line, you just have the left part. But what is line 2? Line 2. Line 2 says A. Line 1 says A, arrow, blah, 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 whatever. But if you have A and A, that's when you eliminate the conditional and you get all the information on the right side. That's how conditional elimination works. From A, then B, and just A, you can get the inference that B. Because again, like just in terms of everyday common sense, if you walk around with no mask, then you will get coronavirus. Take that to be a conditional. And then suppose that someone walks around without a mask, that's the antecedent. According to the conditional, then the consequence that should follow from that is that they get this coronavirus. So 2 facts imply a third. If you have an if-then, and additionally you have just the if part being true, then of course the then part follows. Like, right, watch. If I open my hand, this marker will fall. That's a conditional. Like, so if I do that, if I open my hand, then it will fall. Let's watch. Okay, I open my hand, and then the consequent kicked in because that's what follows from me opening the hand. So when you have an if-then, and then the then part comes after that. This is conditional elimination because A eliminates this conditional on line 1. Does this help a little bit, Jamie? Let me know, because I'm trying to help out and just explain each step very clearly. The third step is conditional elimination. Good. And it's because after we established A, we look back at line 1 and see that that can be useful in eliminating the conditional. Okay, but anyway, my question earlier still has not been answered. What is the goal internal to the scope of this subderivation? What is the goal that we're trying to get to now? We're not just flying blind. Well, A then B, ultimately, yes, Lily, but a little bit prior to that. We just want internal to this subderivation the letter B to appear, because that's when we can close it and write A arrow B. Does this, is this making sense to you? We need B. So anyway, what's the next step? What's the next step? Good, Lily. You say B from conjunction elimination of line 3. So we assumed A, and it took a few steps, but we reached B. That's what we wanted. So that allows us to close this subderivation. When we close it now on line 5, what's the result to write? On line 5, since A has successfully led us through inference to B, we are now permitted to close the subderivation and write what full sentence on line 5? A then B, correct. A arrow B. And please, if you could tell me the justification for this. What's the justification on to the right? That's all I need to know. Just tell me the rule, the citation of the rule, and the line numbers that are off to the right here. Yes, it is conditional introduction involving lines 2 through 4. Okay, good, but we are not done, because if you consider this, we need to have both if A then B and also if A then not D. Okay? Good, Jamie and Lily. So on line 6, another step must be taken. What could that be? You know, because we already did half of this by getting through this conditional. So now you should think about how to complete the rest of the proof, since we have to now attend to the other side of that conjunction. So what can be assumed on line 6? On line 6, tell me what to assume. Come on, people, tell me what to assume on line 6. Yes, good, Leo. Assume A for conditional introduction. Okay, line 7, little limitation of space. I'll try to make sure I get it all in there, write a little smaller now. But on line 7, look, you've got A now. Okay, and what is the goal within the scope of the subderivation here? We're eventually trying to get to, to not D. But Evelyn, we can't just write it down immediately. Like, you have to take inferences to get to not D. So what is an inference that will get us closer to this statement of not D? We've now got A. Every time a new line is entered, look back at the previous lines in combination with the current one. Since you now have A, you have to look at what's available previously and see what you can infer. So correct, Leo. It's, sorry. No, not correct. Let me make one clear statement. And this is something that I was hoping we would get to. So once you close the subderivation, like once we closed it here on line 5, it's no longer accessible. So right now on line 7, lines 2, 3, and 4 are not accessible. It's like a locked vault. They can no longer be touched. So all you have access to are lines 6, 5, and 1. Okay, the subderivation's closed, so you can't reiterate from 3. But good, Amaya, we do have the ability to do conditional elimination on 1 and 6. And that gives us B and not D. Okay, B and not D comes from the combination of this conditional plus line 6, which is still open, where it says letter A. Okay, so line 8, the next line of the proof. We are almost there. We are basically 2 steps, I think, away. But tell me what then can be placed on line 8, because as you guys know, we ultimately need to get this thing established. So line 8 then. Okay, good, Leo. It's tilde D. It is not D, and that comes from conjunction elimination of 6. 6, sorry, no, not 6. 7, thanks. 7. 7 is where this conjunction is housed. And so it is this line that is being eliminated where we're taking tilde D off. So A has led us to tilde D. All right then, so on line 9, it's a little small, sorry for that, but on line 9, what's the result here on line 9? We close the subderivation now because we got to the needed consequence. And that means that the result on line 9 is what? When we close the subderivation. You basically just have to look at the top line and the bottom line, and it's going to be something, arrow, something. Okay, good, Amaya. It's A, arrow, tilde D. That comes from conditional introduction. What are the line numbers? Conditional introduction lines what? 6 through 8, good. Okay, now the final step here is the last one on line 10. Sorry for that, it's a little cramped. I'll try to write smaller next time, but at any rate, on line 10 is the last step. What is line 10? If it's the last step, that's kind of a big giveaway, because the last step is always just whatever you've been told to derive. So what is this final 10th step of the proof? Let's just see it in the chat or hear it from you. The final step. Like, why did we build this and also build that? Okay, good, Amaya. It is the conjunction of the two conditionals, A arrow B and A arrow not D. So you see here, A, if A then B, and if A then not D. And what is our final justification for this? The rule and line numbers that allow this to be entered on the proof. Just last step. What's the justification? It is conjunction introduction. No, Isaiah, it's not biconditional introduction. There's no biconditional in the whole proof. The biconditional is the double arrow. But Isaiah, there's no biconditional. But there is conjunction. This is a conjunction. That's conjunction introduction involving line 5 plus line 9. 5 is A then B. 9 is A arrow, not D. So line 5, comma 9. And that's the proof here. So just to have it cleanly displayed so we can all see that together. Here it is on the screen share, but without the justifications entered to the right. But you see the same order of steps. If we go down a bit farther, oh no, sorry, the answer key is what I got to refer you to here. So sorry, let me get that up. Not that one, actually, the other one, sorry. The student one, yeah, here it is. Okay, so 5.1.2, just got to scroll to the correct part. Yeah, okay, so sorry, here it is. Right here, so yeah, you see the steps. We assume for conditional introduction, A, that allows us to do conditional elimination on 1 and 2, unlocking B and not D. With this, we can then simply take one of the conjuncts off using conjunction elimination. So A leads to B, and thus the subderivation is closed. A horseshoe B, conditional introduction 2 through 4. We move on to try and build the second conditional that's needed in the conjunction. And we start by assuming A. Having assumed A, we can then eliminate the conditional on line 1 again, getting B and not D. And from B and not D can be derived from conjunction elimination. So A leads to B, which gave A then B. In a second case of subderivation, A leads to not D, which gives us A then not D. And on the final step, line 10, we simply conjoin what is available on line 5 and line 9. Notice that 5 and 9 are not contained within the scope of subderivations, and so they remain available at future steps of the proof after the subderivation has closed. So that is the correct answer for A. Okay, so let us try another one of these little problems in the problem set I'm talking about, and that's B. All right, so let's try the next one here. So you see it there written on the bottom. And what it says is derive if A, then if B, then either C or D. Yeah, and then yeah, okay, sorry, brackets. So this is what you've got to derive. It is a complex conditional. It's a conditional where the antecedent is just A, but then the consequent is another nested conditional. So it's like if A, then if B, then either C or D. So let us go on and try and start this one. You have one assumption initially, and that is just that if both A and B, then in that case, C. Okay, so this was a little trickier, and we'll just have to be patient, but let's try to take some steps of inference here. Now, one thing I can tell you is that since you need to build this big conditional, the first thing you should always think of whenever it says derive a conditional is to assume the antecedent of whatever the conditional is. And then from there, just try to do your best to find the right-hand consequence. So if that's our pattern here, then we should begin this proof by assuming what? We can begin the proof by assuming what information or statement? Let me know that in our chat if you can. Line 2, assume. No, not A and B, because no, not A and B, Frida, no, Evelyn, it's not A and B, because that's not what you have to prove. You have to prove A, then all this other stuff, just A. Okay, so A is the assumption. And that is for conditional introduction. Now, let's pause and think about something. Having assumed A, what is our goal? What must be obtained within the scope of A? Like if this is ultimately going to be a closed subderivation that spits out as an output the formula that we want, then what will ultimately have to be found within the scope of the subderivation? We'll need to have what sentence there, which will then allow us to close the subderivation. What do we need to have internal to the subderivation? We start with A, but ultimately we're going to get in the last step of the subderivation to what? Like I'm asking you, what's the goal of starting A? It's not B, no. Because what is to the right of the arrow? What's to the right of this first arrow? Well, B is one of the things that is to the right of the arrow, but it's not the whole thing. It's also not just the letter C either, Jamie. It's not a single letter at all to everybody. It's more than that. What is the big thing that has to be found after we've assumed A? Ultimately, correct, Evelyn, it is B arrow C or D. You don't need that leftmost parenthesis in your sentence there, but that's fine. So we need this whole thing. So what we actually need is another conditional. We need, omit A for the moment, we need this. Now what's the main connective of this consequent? What's the main connective of that statement? B arrow C or D. Exactly, Frida, it's an arrow statement. So we need another conditional, which means that we have to create, are you ready for this? A sub-derivation. We have to have a subderivation within a subderivation, okay? You heard me? So what has to be assumed now on line 3? We have to build another one of these things inside of the big thing that's A. So a secondary assumption must be now made, and that is the assumption of B. Now when you have a subderivation within a subderivation, you have to indent over one more ledger line. And we write now B. And that is assumed for conditional introduction. Why have we assumed B? Because ultimately, what goal are we trying to reach within the scope of the B assumption? Now slide over here. If we're assuming B, what do we need to ultimately find inside of this little guy? C or D, correct, Leonard and Evelyn? So then, we have a goal of C or D. How can we get there? Tell me what we can do. Look at the steps. Think of the rules. You have 3 steps, 1, 2, and 3. How can these things be combined or utilized in order to take us anywhere closer to C or D? Let's think logically here. What do you believe can be added to the proof on the 4th step? The order that we're going in is unlocking further inferences. Now that B is there and A by themselves, and the scope lines of both are still open, so they're both accessible. Neither subderivation has yet been closed. So we have access to all these 3 sentences. Frida, you say conditional elimination, but we can't do it yet. There has to be a step that's just prior to that. Brenna, why it's a sub-subderivation? Okay, Brenna, because we first of all need A arrow all that. But all that is B arrow that. So we have to first do a subderivation for this arrow and a second subderivation for the second arrow. There's 2 arrows. And since we have to build this big if, then we have to do 2 assumptions. Assume A, subsequent to that, assume B. It's only because the consequent of the big conditional is another conditional. It's like a conditional within a conditional. Okay, so imagine you went fishing and you caught a fish. This is actually a reference to a classic story from American folklore that Benjamin Franklin, of all people, was a vegetarian for a while. And one day he was at a friend's house who was cooking fish. And the friend had cut this fish open to cook, and what he discovered inside the fish's belly was another fish. So it's like a fish inside a fish. Because of that, the story goes that Benjamin Franklin converted back to eating meat, because he said, if all these animals eat each other, then I don't see that there's anything wrong with it. And seeing a fish within a fish made him think of that. But anyway, set that aside. The fish within a fish thing is just a graphic visual example of what this sort of is. This is a conditional that's inside another conditional. Okay, so the first big conditional has A as its antecedent. But if you just examine what's on the right hand of this arrow, it's another conditional all by itself. So this is like the little fish within the big fish's belly. We have to assume the antecedent here and then look at what's on the right, and that becomes the goal. But because this right-hand information is a big complex formula with an arrow as its main connective, we then have to make a subsequent secondary use of the same rule to build just this part, and then that will fall within the scope of A. Okay, so back to my question though. What is the inference on line 4? We need to complete this proof with the next 8 minutes. So what's the inference on line 4 that we will make? No problem. Thanks for the question too. But there is a specific inference that we must make now. Okay, so Lily, you say conjoin A and B. Exactly. Line 2 and 3, say A on line 2 and B on line 3. And we then can just combine those together using the rule called conjunction introduction, line 2, 3. Very good. Very, very good. But why do you want A and B? Everyone should be able to see this. Look at the whole proof and consider what A and B is going to let us do now. Because now you've created A and B from the individual sentences A, B. it's good because if you have A and B now as a conjunction on line 4, that enables the application of inferences from the previous lines. So tell me, please, what's line 5? Frida, you had something earlier. Aren't you still thinking the same thing? No, it is not B. B's already there. Why would we do it again? It's already line 3, so there's no need to do that. Yes, Jamie, C. But where is it coming from? Tell me the rule and the lines, please. Conditional elimination, yes, but when you say conditional elimination, you have to say 2 numbers. 2 numbers. So 1 is one of the numbers, but what's the other one? Conditional elimination 1, comma, blank. 1, comma, 4. Exactly, because 4 is where the left part appears. So C is the result there. Okay, that's conditional elimination 1, comma, 4. Okay, there's C. What again is the goal within this B subderivation? Just looking at B as though that's the whole proof. We're trying to get from B to what? To C or D, okay? Well, line 5 says C. What could be written on line 6? Line 6. Keeping in mind that we are trying to obtain C or D. Can we get that? And if so, how? Line 6. Think of these rules of inference. One was learned last meeting that is now going to come into play. Tell me about line 6. C or D, good. From the disjunction introduction rule applied to line 5. Line 5 says C. If you remember, disjunction introduction allows you to disjoin anything that you want at all to an existing statement in the proof. So we are now able to disjoin D to C. Okay, well, if we do that, then what is the result on line 7? B has led us to C or D, as we wanted to do. That allows us to close the sub-sub derivation and write what sentence on line 7? We've now completed the subderivation that started with B and ended with C or D. So the result of that procedure is what sentence on line 7? Let me know. Just line 7. When you close the subderivation, it's an algorithm. There's no debating what it is. It's going to be the first line and the last line with an arrow in between them. Okay, but just you got to tell me what to write down. You waiting for someone else to say it, or you just don't know it? Tell me what it is. Yeah, good, Ruby. It's B, arrow, C, or D. And please give me the rule and lines. That's correct, but just let's get in the habit of citing the justification for that. What is it? Good, Frida. Yeah, it is conditional introduction, not 3,6, but 3-6. That's right. Okay, now on line 8, we started with A, and through this little circuitous route of the second subderivation, we've gotten to B, arrow, C, or D. So A led us to all that stuff. So we're really at the end. What's line 8? And tell me the full statement to write on line 8, plus our justification for that. Even if it's not 100% confident, maybe you'll just take a guess. What do you think is line 8? It's we've reached the end of the proof and of the meeting time. So I just want us to quickly say this. A arrow, B arrow, C, or D. Correct. Good, and that's the derived result that we needed. Just the only thing left is the justification, and it is from Conditional Introduction 2 through 7. It's 2 through 7, Jamie. Yeah, no, I saw that as a typo, I guess. Yeah, you always cite the initial line where the subderivation started, all the way down to where the vertical scope line terminates, which in this case it breaks at line 7. So conditional introduction 2 through 7. And just with the last moment here of class, I'll show you as it's written in the answer key. So 1 second then. Yeah, one more up here. Yeah, so here it is written in the chat, or sorry, on the screen share. We have to get if A, then if B, then either C or D. And we just have this one assumption of if the conjunction of A and B, then C. One first step is we assume A for conditional introduction. Subsequently, we assume B because the right-hand side of the major conditional is a minor conditional contained in parentheses, which also has to be proven in a second subderivation. So we assume B, and now that B and A are both on separate lines, they can be conjoined, as we saw here on line 4, using conjunction introduction. Now, available A and B makes the elimination of line 1 possible, resulting in C. That's what we did here on line 5. On line 6, we simply use disjunction introduction to create the statement that is the consequent in this nested conditional. B led us to C or D, thus closing the second subderivation and releasing B horseshoe C or D. Since this now falls within the scope of our initial A assumption, we have proven through 8 steps the ultimate result. Conditional introduction 2 through 7. Okay, guys, well, we have now developed a little more understanding of a few more rules of inference. There's just 3 more that we will start looking at next week. There's negation rules, there's negation introduction and elimination, and then there's disjunction elimination. So we will go over those next week, but keep in mind that the third homework is due in a week from today, so you've got some good amount of time to continue working on it. Anybody who has any questions or wants to check on their work or anything else, feel free to ask for help from me or from the Logic tutor or from any combination of those, and we just continue from here. I've also graded those midterms, like I said in my announcement to you. I provided the answer key, but of course I will help anyone if they want to know about their individual exam or anything else. So thanks again, everybody. I'm going to close the 2 streams that we have going. So for Zoom, see you guys next time. I'm closing that one. Thank you. And then for the YouTube stream, thanks again, guys. And I will see you back after the weekend. Have a great one.